Okay, just when you think you have understood El Nino, there are always new things that emerge, and this paper argues that the strong 2023-24 El Nino was generated by ocean dynamics. Earlier, there was a paper in 2011 arguing that there is a southern oscillation behavior that is not coupled to the ocean, southern oscillation, not necessarily ENSO or El Nino. And it argued that just with the thermal coupling of the ocean, atmosphere can produce the southern oscillation. Here we are saying the atmosphere is not was not involved in the 23-24 El Nino. Globally, 2023 was the hottest year on record and saw the development of a strong El Nino with widespread impacts. This El Nino event was unusual for its strong oceanic warming yet muted southern oscillation and wind anomalies over the tropical Pacific. This discrepancy is perplexing given the historically close coupling of El Nino and southern oscillation, and so Bjerknes feedback that we all talked about already several times. Atmospheric model experiments show that warming in the Atlantic and Indian Oceans in 2023 and the slow background sea surface temperature trend reduced the surface wind response over the tropical Pacific by modulating the Walker circulation. So Indian and Atlantic Oceans were warmer in 2023, and there was a global warming as well going on for the last several decades, and they do model experiments to try and separate the impact of these trends on the Pacific wind response and show that the 2023 El Nino was basically generated in a very different way. Okay. So we develop a hindcast system that reproduces 87% of the June to December El Nino warming even without a wind stress feedback after April 2023. So the entire life cycle from May 2023 to December into the next year was basically done without strong atmospheric wind response. The intense oceanic warming was primarily driven by the strong buildup of Western Pacific heat content during the preceding prolonged La Nina. When there is a La Nina, the stronger than normal trade winds and ocean is soaking up heat, warm pool is crunched to the west and piling up warm water. This indicates that the 2023-24 El Nino primarily arose from oceanic processes independent of the classic positive Bjerknes feedback mechanism. Due to the strong ocean memory, this event was highly predictable at long time leads. So models did a very good job. In fact, climate model simulations suggest that such 2023-like El Ninos may become more frequent in a warming climate. These are kind of almost obligatory statements these days because it says may become more frequent. This kind of a statement was made for Central Pacific El Ninos back in 2009, which hasn't materialized as such. So we have to be careful, but quickly jumping to some figures, comparing the 2023-24 El Nino sea surface temperature anomalies and sea level anomalies, warm SSTs of course, but the cold classic SST pattern is missing, but you can see these in other El Ninos. This is the average of 82, 97 and 2015 El Ninos. Strong warming, strong sea level signal, deeper thermocline, higher sea levels, shallower thermocline, colder SSTs, and mean sea level pressure and wind response was much more muted, weaker trade wind anomalies and very weak westerly wind anomalies, whereas this is what you typically expect. Weak trade winds, so sea level pressure is in colors, so that's a high sea level pressure, low sea level pressure compared to warm SSTs, high sea level pressure associated with cold SSTs, strong westerly anomalies, and of course you can look at the zonal wind anomaly and Nino 3 relations, strong trade winds during La Nina, weak trade winds during El Nino, so 82, 83, 50, 2015, 16, 97, 98 are here with positive Nino 3 and and 23 is down here with hardly any wind anomalies corresponding to the strong Nino 3. And similarly, southern oscillation 23 was not very negative, slightly negative compared to others. Southern oscillation, Darwin and Tahiti is negative when there is an El Nino. Tahiti drops in sea level pressure and Darwin increases, which is what we are looking at here. So obviously it was different. If you look at the evolution of the 23-24 El Nino and the composite El Nino based comparable events that we mentioned already, you are looking at starting here in February of 23 going into 24. This is wind stress anomalies and rain. I have chopped off the longitude here, but you are going from Western Pacific into the Eastern Pacific. So 23-24 evolved as expected, some westerly wind anomalies, weaker trades, and you had rainfall anomalies associated with them, much weaker than the other El Niños of comparable size, 82, 83 to 2015-16. Sea level anomalies and SST anomalies we already saw, but we are looking at the Hofmüller diagram, so evolving in 23 into 24. So you can see that the sea surface temperature anomalies evolved from the east towards the west, whereas these went more the other way. They got very strong in the peak of El Nino, December, January, February. Not so strong. The sea level anomalies were strong here, as we saw before, and negative on this side. So high sea levels, low sea levels, similar pattern but much weaker. If you look at the vertical sections of 23-24 for January, February, March, April to October, and November, December, January, climatological thermocline slope and the El Nino slope. In the beginning, January, February, March, you have warm waters creeping in, the discharge phase, which is further advanced for the other El Niños, and the thermocline was getting deeper compared to climatology. April to October, the thermocline did get deeper here for 23-24, but you can see it's deeper and warmer anomalies here, and it's shallower here than here. So the slope didn't change much here, but it changed here, which is very clear in the peak phase. So you can see the flattening of the thermocline for El Niños, which we expect spread of transport, discharge of the warm waters, entire tropical thermocline is lifted, which is very clear here, but not so clear here. So I'm skipping the captions because explanations are pretty clear. The experiments they did are very interesting. They basically look at how trends in the Atlantic and Indian Oceans and the Pacific can explain what happened in terms of wind anomalies and how the El Nino got initiated. In 2023, North Atlantic and Western Indian Oceans experienced record-breaking warming. You can see the supplementary material. They could potentially affect the atmospheric anomalies over the tropical Pacific Ocean. So to explore this possibility, they conducted 3 AGCM experiments, atmospheric GCM experiments, forced by Pacific detrended SSTA, APAC, Indian and Atlantic detrended SSTA, so atmospheric Ind-Atlantic experiments, and the background SST trends for 1982 to 2023 removed. This approach allowed us to assess the impacts of the Pacific and Indian Atlantic detrended SSTAs and global SST trends respectively. So here we are looking at the responses. We are looking at the Hofmüller diagram again going from 23 into 24, looking at winds here in the control experiment where Pacific SSTAs are removed, Pacific trends are removed. So you see that there are wind anomalies here induced by warmer Atlantic and that's the control run. Let's make sure I don't want to mess this up. The First one is Pacific detrended SSTAs APAC. Second one is Indian Atlantic detrended SSTAs, and third one is background SSTAs removed. So you have, oops, I went backward. You can see this is the control run, Atlantic and Indian trends removed, and this is the vertical circulation associated with those. So you can just see that in the control run, you have removed the Pacific trend, so you are expecting the westerly anomalies and becoming stronger, but you still, so here you have to be careful because you are growing from the 0 degree longitude Greenwich meridian back to Greenwich meridian. So you have the Africa and India over here, and the Indian Ocean coming into the Pacific, and the Atlantic Ocean is here. And maybe I can just skip and say that the experiments show that the Atlantic and Indian warming trends were able to produce Walker circulation perturbations to produce the observed wind anomalies during 23-24, which we saw here. This is tau x for 23-24. See how differently it evolved. And here also we are going only in the Pacific, whereas here we are covering all oceans. Okay, so I'm going to skip this very patchy figure looking at the Hofmüller diagram of how winds evolved, and we'll just read the text on what the interpretation is. To reveal the key physical mechanisms for the strong oceanic warming of the 23-24 El Nino, we conduct a mixed layer heat budget analysis based on reanalysis data, so that's not from models. Extended data, figure 3a, shows that we don't have the figure here. The vertical advection drives Nino 3 warming during June to December. So it's an ocean dynamic process where for vertical advection to drive warming, you basically need deeper thermocline and warmer subsurface subsurface temperatures. Usually upwelling brings up the thermocline and cold waters, and then entrainment happens. SSTs cool. But if the thermocline has deepened because ocean dynamics has spilled the warm water and trades are a little bit weaker, so you are upwelling doesn't go to zero, but you are entraining warmer waters. That's what they're talking about. And then you also have the horizontal feedback. So the vertical thermocline feedbacks are combined with Ekman feedback in the horizontal. So large surface warming was observed in the equatorial Pacific during June to December 2023, which the mean upwelling pumps into the mixed layer, raising SSTs there. Additionally, the reduced upwelling due to the weakened trade winds that I just mentioned contributes to SST warming through Ekman feedback, which means the horizontal transports are also adding to the warming. So you have vertical term, horizontal term adding, which is very different than the classic Bjerknes feedback, where you have thermocline getting deeper because of trade winds getting weaker, SSTs getting warmer, sea level temperature gradient and pressure gradient getting weaker, winds getting further weaker, thermocline getting further deeper, and so on. The slow ocean dynamic adjustments imply that 2023-24 El Nino can be predicted at long leads, as ocean heat content carries memory and serves as the major source of predictability. El Ninos are events that happen over 9 to 12 months. Very few of them extend into the next year. 2014-15 did, and then there are a few others before, but La Niñas can persist for multiple years, and there are papers explaining why that can happen. Recharge can go on for multiple years as it did during 2020, 21, 22. Then 23 came in and used all that built up heat content to drive this ocean dynamic El Nino. Okay. Indeed, the recent studies noted that skillful predictions of the 23-24 event, but the underlying physical processes and the unique air-sea characteristics of this El Nino have not been previously fully explored through diagnostic analysis and insightful model experiments as done here, of course. And large ocean heat content stored in the Western Pacific following the 3-year La Nina. Most models predicted the El Nino at the beginning, so they used the stored heat as the initial condition for their El Nino predictions and said El Nino is coming, and they were of course right. So high predictability basically came from the ocean built up heat, and then Bjerknes feedback may have been done wrongly in the models, which in the real world was much weaker. So when initialized on April 1st, 2023, the predicted Nino 3.4 SSTA for December 2023 was 1.64 degrees C. For Nino 3, it was 1.73 degrees C. Closely matching the observations. Okay, so here they are looking at the experiments again in terms of the different couplings. So here simulated control and observed SSTs are closely matched during January 82 to December 2023. So the model is able to produce the observed Nino 3 given the observed model initialized experiments. Okay, in B, we are looking at simulated Nino 3 SSTAs from the control, April 23rd initialization, and their difference, that is wind 20. So basically in this experiment, they remove the coupled model winds and give it the observed winds, or they do some kind of a smoothing to argue that with the without giving coupled winds, the El Nino was still able to be produced, just confirming their hypothesis that without having coupled wind feedbacks, just with the thermodynamics of the ocean and ocean dynamics, vertical and horizontal thermocline Ekman feedbacks, they could reproduce the 2023-24 El Nino. I'm being brief there because the experiments are kind of hairy. So what are the insights into ENSO dynamics? Statistical analysis of historical events has led to important advances in understanding the coupled dynamics of El Nino and its flavors. Our observational analysis has shown that the 2023-24 El Nino was peculiar. The atmospheric responses to the strong equatorial Pacific SSTA were weak compared to those inferred from historical events. This suggests that the Bjerknes feedback was not fully established to promote the growth of this strong El Nino, a surprising result against widely accepted ENSO theory that centers on this coupled feedback mechanism. Through advanced GCM experiments, we show that even in the absence of tropical air sea feedback or the southern oscillation component, ocean dynamics alone can generate a strong El Nino. That's the main message. Amy Clement's message in the thermally coupled Walker mode was that without ocean dynamics, southern oscillation could be produced by atmosphere and ocean thermodynamic coupling. Here they are saying without atmospheric coupled feedbacks, southern oscillation feedback, ocean dynamics alone can generate an El Nino. Climate models project that the occurrences of 23 like El Nino increase markedly in a future warmer climate, primarily due to more frequent strong positive sea level anomaly events in the Western Pacific, which is the multi-year La Nina like build-up. These strong SLAs result from a more pronounced sea level response to wind stress, potentially linked to factors such as reduced wave damping due to faster phase speeds from enhanced vertical stratification or the nonlinear thermal expansion of seawater. Further research is required, of course. We are making many claims there. Remember, models have biases, deficiencies, in the Eastern Pacific. They are not reproducing the observed trends in the real world. Ocean in the Eastern tropical Pacific is cooling, whereas models don't do that so well. They have other issues like double ITCZ, etc. But given all that, models are self-consistent, or there is a consensus among models that with global warming, stratification is going to get stronger, so that's going to affect the wave speeds in the ocean, which depend on the density and vertical profiles of density, etc. And that's going to lead a cascade of how sea level will respond to winds, how heat will build up and sea level anomalies will build up, and they are saying 2023 El Nino was maybe an indicator of how the future El Ninos may look like. But we have right now 2026 El Nino evolving with very strong feedbacks and looks like the previous El Ninos. So it's not contradictory in any sense, because when climate change affects things, it's not like every El Nino will look different. It is that more El Ninos will begin to look like the 23 El Nino potentially. That's the claim. But you will still have original type El Ninos in the middle. It's just that you shift the probability density function. Okay, let me leave it here. I wasn't very detailed, but you can read the paper. The main message is that without strong atmospheric coupling, because of the Indian and Atlantic Ocean warming and the buildup of heat in the West Pacific due to the multi-year La Nina, there was probably a ocean dynamic dominated El Nino in 2023, which raised a lot of publicity, which because of the warming. And now 26 will again cause warming, 27 will again probably cross 1.5 degrees C threshold, and so on. So we just wait and watch. Okay, see you.